So in a previous video, we worked out a formula from the definition of the Taylor series to compute or work out the Taylor series for sine of x centered at pi over 2. And we did that just by the definition of the Taylor series. So remember that the definition of a Taylor series is that it's equal to the sum, n goes from 0 to infinity, fn applied at the center point over n factorial, that's a derivative, right, times x minus x naught to the nth power. This is the definition of the Taylor series. If you can do it, this will always work, right? But what I mean by if you can do it, if you can work out a formula and notice a pattern for these coefficients, if you can do that, then you're good to go, right? This will always work. Now, frequently though, there's a number of Taylor series that we're gonna use so much that we memorize them and we know them well, especially some of the Maclaurin series. And so what we can do is we can use known power series, known Taylor series, to build Taylor series for other functions, right? If we know a relationship between these functions. And in a previous video, we worked out that the Maclaurin series for cosine of x is equal to the sum, n goes from 0 to infinity, of negative 1 to the power n over the even terms factorial, so 2n factorial times x to the 2n. All right, and it's an exercise that you guys will do to prove that this is true. This converges. Okay, this converges to the value of cosine of x. The sum equals cosine of x for all real numbers. So for all x in the real number line. All right. Once you learn something like this, and you know that the Maclaurin series for cosine is something like this. So, you know, your perspective will change as you get more familiar, more comfortable with these. But this is a really nice series, okay? This is very nice. It's not too crazy to write down. It's only the even terms. It's well behaved, right? So once we know this, and we memorize this, we can use this to build other series, especially because of this fact, okay? It converges for all real numbers. And it turns out that, let's not get into this now, but it turns out that actually this converges for all complex numbers as well to the proper value. And now you have to do some extension there, right? So this is question mark, maybe a little weird. What we care about is that it converges for real numbers, all right? So here's the deal. We want to try to find the Taylor series for sine of x centered at pi over 2, all right? So not the Maclaurin series. The Maclaurin series is for cosine is this, right? Centered at 0. We want to find the Taylor series for sine that's centered at pi over 2. Like I said, we worked this out by definition in the previous video, but let's do this one using just basic trig in this video, okay? So one basic fact of trigonometry that I'm sure you remember is that if you have an angle, so remember cosine x on angle, so if you have an angle x and say a right triangle, you have an adjacent, you have an opposite, you have a hypotenuse, right? And the cosine of this angle x is equal to the adjacent over the hypotenuse. And I've labeled these this way because they're in relationship to this angle that I've chosen, right? Cosine of x. They're in relationship to this angle x. So that's adjacent to side x. But there's nothing wrong with this angle up here. So this angle, let's call it like the Greek letter phi. So in terms of this Greek letter phi, capital A is actually not the adjacent side. It's the opposite side, right? And so this A over H, this same ratio, is actually equal to the sine of this angle, the opposite over hypotenuse, right? So this is equal to the sine of phi. And so at this point, what do? You get rid of the middleman, right? And you set these equal to each other. You say, all right, well, the cosine of this angle x is equal to the sine of this angle up here. But what's this angle? Well, we know that the angles of a triangle have to add up to pi, right? So we have pi. It must equal x on one hand plus the right angle, which is pi over 2, plus the angle up here, which is phi, right? So all the angles in a triangle add up to pi. Now we can subtract through pi over 2. I mean, we know this identity, but it's always fun to review, right? And so what we can learn here, by just a little rearrangement, we can subtract pi over 2, we can subtract x. Phi is equal to what? Pi over 2 minus the angle x, right? And so what we learned, this is called the cofunction identity, that the sine of the angle pi over 2 minus x is equal to the cosine of x, right? So the sine of pi over 2 minus x is equal to the cosine of x. Now, that's not exactly what I wanted here. I kind of went backwards. So the other cofunction identity, so and here. This could all work if we use the other angle, right? The other side, opposite and hypotenuse. The other cofunction identity is that the sine of x is equal to the cosine of pi over 2 minus x. And this is actually the one that we want. And the reason is because we're trying to find a representation of sine of x, not sine of pi over 2 minus x. So this is the one that I should have started with, but it's okay. So these are both cofunction identities. And the reasoning is exactly the same, except you start with the opposite side, right? So look what we can do. We can go here. We can take our we can take our sine function, set it equal to its cofunction, right, cosine, and then plug in this value, pi over 2 minus x, into the x here, right? So whatever substitution we make here, we do it on the right-hand side as well. And we're going to very quickly get the Taylor series for sine of x that we want. So let's write it out. Sine of x is equal to, by cofunction identity, cosine of pi over 2 minus x, which, if we plug this into its Maclaurin series, where we treat this like the argument, then the Maclaurin series says this is the sum, and goes from 0 to infinity, negative 1 to the n, over 2n quantity factorial times, now here's where the green comes in, right? Instead of just x to the 2n, we get pi over 2 minus x to the power 2n. All right? And if you compare this with what we worked out in the previous video for sine, for the Taylor series for sine, centered at pi over 2, this is close, but it's not exactly right. And it's right, but it's not exactly the same the way it looks. What's the difference, right? The difference is that usually we have x minus the center point. We need this actually, right, for this to be correct. We need this to be the case. So we come back down here and we look at this and we notice, all right, the powers of the exponents here, the exponents on the terms are all even. And when you take a power of an even, you take an even power of a number that's a difference, right? That's either, it could be negative potentially. This is an even function, right? I'm having trouble spitting this out, but you can reverse the order and it doesn't affect the sum. All right, and so this 2n tells us that we can reverse this and we can write down the exact same answer that we got on the previous one, right? The previous time that we worked out this Taylor series for sine of x, and we get then that the power series for sine of x centered at pi over 2 is the sum of the even terms, so negative 1 to the n over 2n factorial x minus pi over 2 to the power 2n. All right, this is equal to sine of x. And that's exactly what we found the other way. This time we used our known Maclaurin series for cosine to help us. We got the same answer. Pretty awesome.